This actually was the previous exam question, one of the small questions. We take a function on R3 with values in RQ. The origin, 0, 0, 0, well, that's clearly an interior point of the domain. We assume that, we took it at 1, 1, 1, I guess, okay. Assume that f is differentiable, but every point in R3 is an interior point. F is differentiable at the point 1, 1, 1. Now we were given the values of the directional derivatives at 1, 1, 1, but in the direction of different vectors. So I guess the direction in 1 was 1, 1, 0. This was A. Then we had F1, 0, 1, 1, 1, 1. We refer to that as B. And finally, F1, 1, 1 at 1, 1, 1. We decided to denote this by C. A, B, and C are members of RQ. They're Q vectors. The question was, find df at 1, 1, the derivative of f at this point, evaluated at minus 1, 0, 2. Well, no, it was, I guess, it makes no difference, but let me take exactly what we had before. Okay? Now we will use two things in solving this. One is the relationship between directional derivatives and the derivative of the function at various points, plus that this df1, that's a linear map. So if we can write minus 1 to 0 as a linear combination of 1, 1, 0, 1, 0, 1, 1, 1, 1, well, these three vectors are chosen to be linearly independent, so they form a basis for R3. So this can be written as a linear combination of them. First, let's do that. Now, set minus 1 to 0, we wish to write it as C1 times 1, 1, 0 plus C2 times 1, 0, 1 plus C3 times 1, 1, 1. But this leads to three equations. Now, the first one is C1 plus C2 plus C3. That's supposed to be minus 1. Then C1, this is nil, plus C3. That's supposed to be 2. And finally, this is 0, C2 plus C3. This is supposed to be 0. But we can easily solve this. If C2 plus C3 is 0, if we take it with this, C1 will be minus 1. If C1 is minus 1, C3 will be the negative of that. That is 1. And here, C2, oh no, it's the negative of C2, not this. well, from here, C3 will be, this is -1, C3 will be 3, and C2 will be the negative of that, -3. Okay? So df 1, 1, 1, evaluated at -1 to 0, this is what we're supposed to find. Well, this will be equal to df at 1, 1, 1 of the linear combination of this, where we have -1 times, the first vector was 1, 1, 0, then C2 is -3, well, here, -3 times the second vector, that's 1, 0, 1, and then C3 is 3 times this vector, which is 1, 1, 1. But now we can use the linearity of this function. This is a linear map on R3 with values in RQ. So this is equal to -1 times df 1, 1, 1 of 1, 1, 0 plus -3 times, so let me write it directly as -3 df at 1, 1, 1 of 1, 0, 1 plus 3 times df at 1, 1, 1, also evaluated at 1, 1, 1. Well, so the problem boils down to finding these q vectors in terms of A, B, C, but this is equal to the directional derivative of f in the direction of 1, 1, 0 at 1, 1, 1 plus or -3. Now this is equal to the directional derivative of f in the direction of 1, 0, 1 at 1, 1, 1 and plus 3 times the directional derivative of f in this direction and at the same vector. But these are nothing but the quantities given here as A, B, and C. So the answer turns out to be -A minus 3B plus 3C. Okay? Let us consider another example. Any questions to this example? Now let us define f on R2 to R as follows. F of xy, we'll take it as x over y if y is different than 0 and 0 if y is equal to 0. Now we will show that this function at the origin at 0, 0, it owns both partial derivatives, but unless a vector is a multiple of one of the two basis vectors, standard basis vectors in R2, then the directional derivative will not exist. It will own partial. Will it be differentiable in that case at 0, 0? No, well, if it's differentiable at some point, then if it's an interior point, as all vectors would point into the set of the domain, into the domain at that point, then differentiability implies existence of all directional derivatives. If some directional derivatives do not exist, that implies that the function is not differentiable. Now let us first find this at 0, 0. If this is well defined, then it will be equal to the following limit. 1 over t. Now here we have f of a plus tu. The point A here is 0, 0. T. But since we're taking the partial derivative with respect to the first variable, the direction should be taken as E sub 1, the first standard basis vector in R2, which is 1, 0. Then this minus f of 0, 0. Now let's check whether this limit exists or not as t tends to 0. If it exists, this will be 1 over t. Now this is f of t0 if we perform this addition, but the value is 0 in that case because the second component is y is equal to 0. But let me write it in two steps, f of t0 minus f of 0, 0. But this is 0, this is 0 as well. So this is nothing but the limit of as t tends to 0, 0 over t, but that's 0. Okay? So as this limit exists, it's equal to this. Now likewise, let's consider its partial derivative with respect to the second variable. Now, well, let's first check whether the limit exists corresponding to this partial derivative. But this time we'll have, this is the point at which the partial derivative is considered. Now this time it's in the direction of 0, 1. This minus f of 0, 0. So this is equal to limit 1 over t, t tending to 0. This time, this is f of 0t minus f of 0, 0. Now this is equal to 0 since the second component is 0. Well, here the second component is not 0, t, but it's in that case x over y, 0 over t. This will be 0 again. So this again will be the limit of 0 over t as t tends to 0. This is equal to 0. So both partial derivatives exist and they're equal to 0. Now, let us consider any u, any direction, which is not a scalar multiple of either 1, 0 or 0, 1. But that's equivalent to saying that both components, if you take u, u1 and u2, they both should be different than 0. If one of them is 0, then it will be a multiple of these and will have the same result. Now, let say alpha beta be in R with alpha and beta both different than 0. Set u equal to alpha beta. The question is whether f sub u at 0, 0. The directional derivative of f at 0, 0 in the direction of u, where u is given by alpha beta. Now let's check the same expression for this u now, and check whether it has a limit when t tends to 0. Now we'll have f of the point at which we consider the directional derivative is 0, 0 plus t alpha beta, and this minus f of 0, 0. But this will be equal to 1 over t. This will be f of t alpha plus t beta, and well, that will be minus 0. Of course, when we take the limit as t tends to 0, we never consider t equal to 0. So we have this for all t different than 0. But then this will be 1 over t times t beta. Beta is different than 0, t is different than 0, will be different than 0. So according to that, it will be t alpha over t beta. But this will be alpha over beta, these t's will get cancelled, divided by t. But now this is a non-zero number. Well, as t tends to 0, this has no limit. Has no limit as t tends to 0. Well, as this limit does not exist, so our conclusion is, so f sub alpha beta at 0, 0 does not exist. Well, hence, f is not differentiable either. Okay. Well, you might now ask, well, that's fine, but what about if at some interior point of the domain, all directional derivatives do exist? Does that imply that the function is differentiable? Well, in the exercise set, you have an example, well, where all the directional derivatives exist, but yet the function is not differentiable. So here, most of the directional derivatives did not exist. This, of course, implies that the function is not differentiable, but the existence of all directional derivatives, that does not imply differentiability. But when we introduce a useful notion, well, in order not to have to resort to the definition all the time, in order to make that notion user-friendly, well, we need to find some equivalent ways and some ways of expressing that notion in terms of more familiar notions, which are easier to check or easier to handle with. Now, for that, let's just go quickly to some basic linear algebra. Now, let T on Rp to Rq be a linear function or a linear map. Makes no difference. Well, then we can represent this linear map by a Q by P matrix with respect to the standard basis vectors, but that's not only the case. If one basis for this and another basis for RQ is given, then we can represent it again by a Q by P matrix, which represents this time with respect to the given basis. But let's confine ourselves to representation by standard basis. Now, there is some Q by P matrix, say C, such that for all U in Rp, we have T of U is equal to C times U, but now we have to make clear U is a member of Rp. This is a Q by P matrix. Well, here we represent U as a column matrix, as a P by 1 column matrix. Well, then you obtain this as a Q by 1 column matrix. But we will make no distinction between column matrices, row matrices, and vectors. But let me write that where U and TU stand for, the first one is P by 1 and Q by 1 column matrices here. But if we can do for any linear map, well, if you have F on A to RQ with A non-empty subset of Rp, A in A interior, F differentiable at A, well, then dFA, that again will be a linear map on Rp to Rq. So there is also some Q by P matrix as above, representing dFA with respect to the standard basis vectors or bases, standard of Rp and Rq. What that matrix will be, do we have some information already, at least for some cases for P and Q? Now let's go back to our last corollary. It was in short as follows. We took some non-empty subset of Rp. We took a function on A to R because we wanted to deal with partial derivatives of f. Then we took A in A interior. We assumed that f is differentiable at A. This implied that all the partial derivatives of f at A exists, and moreover, we have that for any U in Rp, dFA evaluated at U turned out to be just the various partial derivatives of f at A, where each partial derivative was multiplied by the corresponding component of U sub I, when I runs from 1 to P. But as you see, this is nothing but the matrix, raw matrix, multiplied by this column vector. Here, dFA, since this is on a subset of Rp with values in R, dFA, that will be a linear map on Rp with values in R. But then according to this, a Q by P matrix, that will be a 1 by P matrix. So this is actually nothing but the 1 by P matrix, which represents the derivative of f at A with respect to the standard basis vectors of Rp and R respectively. Okay? Now, but we wish to generalize this. Well, what happens when we have here Rq? Now let's set to do that. But now, in order to relate the derivative of a function on Rp with values in Rq to what we know here from this corollary, well, we can actually separate a function from Rp to Rq, or from a subset of Rp to Rq, into Q different real-valued functions, the coordinate functions. Well, f1 of A, f of A, that's a Q vector. f1 of A will be the first component of that Q vector. f sub I of A, that will be f of A, but the ith component of that. Let's first define that. Now let A be a non-empty subset of Rp, f on A to Rq, a function for each I from 1 to Q, the ith coordinate function f sub I of f is defined by fi on A to R, where at each, well, f sub I of x, now you will form f of x, that's the Q vector. You take the ith component of that at each x in A. Now, if this function at an interior point of the domain cap A, if it's differentiable there, it is standard and easy to show that all the coordinate functions are differentiable at that point. But a real valued function being differentiable, we have this representation. So hopefully we can actually assemble together the representing matrices of the coordinate functions into one big matrix which represents the original function itself. So first, a proposition. Here we have this, a non-empty subset of Rp, a function here. Assume that A is an interior point of A and F is differentiable at A. Now, for each I, from 1 to Q, F sub I is differentiable at A. Well, this means, in particular, bringing this together with our preceding corollary, all the partial derivatives of F sub I with respect to all the variables, they all exist. Now, the proof of this is a good exercise. I'll leave that to you. But now, well, for F1, this will be the representing matrix. For F2, well, it will again be a raw matrix, but F1 being replaced by F2. So, well, then we expect actually the Q by P matrix, whose ith row is given by the representing matrix of the ith coordinate function, to represent the entire function. But what's the name if I have such a function? And at A, well, if I form first, this is the first row with F1, the second row with F2, and so on, the last row with FQ, what's the name of that matrix? That's the Jacobian matrix of F. Now we'll see that the Jacobian matrix of F, in case F is differentiable, because the Jacobian matrix, the partial derivatives all may exist, the Jacobian matrix may be well defined, but if the function is not differentiable at that point, then well, there will be no linear map to be represented. But if the function f is differentiable, then it will be represented by the Jacobian matrix. So let's define the Jacobian matrix first. Now let A be a non-empty subset of Rp, f on A to Rq, a function. Assume that A is an interior point of A. Now here, in order to define the Jacobian matrix, the only thing we need is that the partial derivatives exist at this point. And del Fi, del xj at A exists for all coordinate functions, that is I from 1 to Q, and all variables with respect to all variables, that is j from 1 to P. The Jacobian matrix J sub Fa of F at A is defined by J sub Fa equal to, now the first row is del F1, del X1 at A, del F1, del X2 at A, up to del F1, del XP at A. And the last row, that's the Q coordinate function, del FQ, del X1 at A, del FQ, del X2 at A, up to del FQ, del XP at A. Now, of course, if P and Q are equal to each other, then we can also take the determinant of this. In fact, by Jacobi, this was first defined as for the case when P is equal to Q, and well, whether this matrix was non-singular or not, so the determinant was zero or different than zero. So in fact, in calculus, the Jacobian of F at A, that refers to the determinant of JFA, where P and Q are equal to each other. But here, in order to distinguish that, well, we refer to the Jacobian matrix. So, well, let me also write that part. P is equal to Q. We refer to the determinant of JFA as the Jacobian, but we will also use determinant explicitly, which is also denoted by del F1, Fp, Q and P are equal to each other, del X1, Xp, this, this when X is equal to A. Well, when I was a student, this was the symbol in advanced calculus books used for the Jacobian determinant, but I do not know whether that continues, but I guess so. I mean, these are, okay. Well, now we can actually write and prove our theorem. We are ready to do that. If you have no questions so far, theorem. Let, again, a non-empty subset of Rp, F on A to Rq, a function, assume that A is an interior point of A and F is differentiable at A. Now, for each U in Rp, we have that the f of A evaluated at U is simply the matrix product of JFA with U, where this U is a column matrix, but then it yields this as a column matrix as well. But we'll stick to this well. We can represent vectors as column or row matrices or column matrices. They can be considered as vectors of the corresponding dimension. Proof. Now first, what can you tell about the function from Rp to Rq, which sends each U in Rp to this matrix product? This is a Q by P matrix multiplied with this. Well, that will yield a Q vector, and that, of course, function will be linear. Well, each linear function on Rp to Rq can be represented via a Q by P matrix. And conversely, when you start with the Q by P matrix and define the function sending you to this product, that will be linear. Okay, that's a basic result from linear algebra. Now, the function associating with each U in Rp the vector J sub f of A times U in Rq is a linear map from Rp to Rq. Why do you think this observation will be useful here? Remember the definition of differentiability. Well, we defined it as the existence of a linear map from Rp to Rq which satisfied the given condition over there. And then, although we omitted the proof, we are allowed to use it. Well, the next proposition was, well, a function could have at most one derivative at a given point of its domain, either no derivative or if there is some such linear map which satisfies the definition of differentiability, then it has to be unique. Thus, if we use this function, sending each U to this product, and if that satisfies the definition of differentiability of f at A in the A interior, then that will be the derivative. Okay? Okay, then let's start to do that. But for that, well, we'll start with an epsilon greater than 0 be given. Then there should be some delta positive, which does the job. The inequality in the definition would be satisfied for all x in the delta ball about A intersection cap A. Okay? Okay. But let us also, before doing that, let us also note if f is differentiable at A, all the coordinate functions are so. Note that f sub I is differentiable at A for each I in 1 to q. Now let epsilon be greater than 0. But again, we know what the matrices representing the derivatives of f sub I are. Well, the whole thing is to bring them together. So let us use that f sub i's are differentiable, and let us also use that this row matrix, that is what represents the derivative of f sub I at A. Okay. Since f sub I is differentiable, at A, and epsilon over q is positive, there is some delta I positive such that for all x in delta I ball about A intersection A, we have f sub I of x minus f sub I of A minus df sub I A at x minus A less than or equal to epsilon over q times x minus A. Well, in fact, this norm here is the norm in R. Thus, this is just the absolute value. This is the norm in R P. X and A are in there. And we know that this is equal to just the partial derivatives of f sub I with respect to xj at A, xj minus aj, and this j from 1 to p. This is just the last statement while we converted that to this form. Okay. Okay, now here we have Q inequalities. We wish them to combine into one, which will yield this equality. So, well, I guess this is a nice place to stop. Let's have a break and then continue next hour.